So do you hear me?
Yeah, great. Okay, so great pleasure to have Tsachik Gelander from Weizmann Institute today, and he's going to give us two talks. And today's talk is on invariant random subgroups and their importance in the context of lattices. All yours, Tsachik.
Thank you. Yeah. So just a minute. Okay. So yeah, thank you for the invitation. Actually, I never been in Bombay. I spent 8 years ago. I spent 2 weeks in Tata Institute in Bangalore, where I gave 12 lectures, seminar about homotopy type of locally symmetric spaces. And I'll be happy to visit when it's possible also in Bombay. So actually I'm now in Budapest in Rainy Institute, and they gave me this smart camera room to give a talk, but there is no crowd, so only you. So this talk will be about invariant random subgroup. And actually more about applications of invariant random subgroups to the theory of lattices and locally symmetric spaces. And next week, I will give a second talk about non-invariant random subgroup. So we will see that invariant random subgroup is a great tool to study lattices, but then it has some limitations. So about 10 years ago, people realized that invariant random subgroup, which in short is IRS, is an excellent notion which is very valuable to study several properties. So in particular, my interest is in lattices in semisimple Lie group and locally symmetric spaces. So let me start by definition. And ask me a question whenever anything is not clear. That's one of the disadvantages of this kind of talk is that the speaker even have less connection with the audience. So I don't know how much you know. So yeah. So let's start with let G be, let's say, a locally compact group. So we denote by sub G the space of a closed subgroup. All closed subgroup of G, and there is a natural topology, which is called the Chabuti topology. The Chabuti topology. I will say something about it in a moment. So maybe we start with a few examples. So if G is R, example, if G is R, then what is a closed subgroup of G is either the trivial group, which is 0, or the full group, or some multiple of the integer. That's all closed subgroup of G. And the topology, which I still didn't define, but you can imagine when two closed subgroups are closed. So if I take alpha very small, you will get a discrete group which get closer and closer to this. And if I take alpha very big, you get a discrete group which get closer and closer to this. So with the topology, it's homomorphic to an interval, to a closed interval. Another example is if you take G to be R2, you still see when I write here? Do you see this?
Yeah,
Yes.
Then it turned out that sub G, it's more complicated, but it's homomorphic to a sphere of dimension 4. It's a theorem, I forgot by whom, two people. And in general, if you take a general group, so for instance, if you take G to be SL2R, it gets very, very complicated. So sub G, the space of all subgroup, it's a very complicated topological space. But it's still compact, it's always compact. So that's a proposition. Sub G is always compact. So you have at least a compact space to work with, but complicated one. So let me at least say something about the Chabuti topology. So there are several ways to define it. Let's say the fastest way is by introducing a metric. So the distance, so let D be, let's say, a proper metric on G. And then you can say that the distance, the Chabuti distance, let's denote it by rho, between two groups, H1 and H2. I define it to be the integral of the Hausdorff distance between the intersection of H1 with a ball around the identity of radius R and the intersection of H2 with the same ball. And then I integrate and I multiply by some function that decays fast, so this integral will converge. And this, so you see that two groups are close to each other if the intersection with very large balls are close in the Hausdorff distance, roughly. So that's the Chabuti topology, and it gives you a compact space associated to G. But this compact space is usually, as I said, very complicated, so it's not very helpful. So once you have a too complicated space, it's natural to consider probability measure on this space and take random point, and then we may hope we will be able to say more. So yeah, this space is too detailed, so we want to lose some details. So G acts on this compact space by conjugation. And then I can define an IRS, an invariant random subgroup. An invariant random subgroup is just a probability measure here, which is invariant under this section. So the definition, the most important definition for today's talk is that an IRS is a G invariant probability measure on that space, on the space of closed subgroup. So in a sense, it tells you a law how to pick at random a subgroup, and this law should be invariant under conjugation. So that's an IRS, and yeah, let's see some examples. So First, what are Dirac measures? So, example. So, Dirac measure correspond to normal subgroups. So if you have a Dirac mass on some subgroup H, it means that H, this is an IRS, if and only if H is normal in G. So that's first example. So in a sense, invariant random subgroup is a generalization of normal subgroups. Second, if gamma in G is a lattice, should I define a lattice?
Yeah, maybe, because there are people from many places.
So a lattice, so that is G mod gamma admits a G invariant measure, G invariant probability measure. If G mod gamma admits G invariant probability measure, where the action on G on this cosset space is just by left multiplication, then we say, okay, for lattices, we also assume that that gamma is discrete and gamma is discrete. But in general, to define an IRS, you just need that this as a probability measure. And then you have a map. So let's suppose you have a probability measure mu on G mod gamma. And then you have a map from G mod gamma to sub G, to this compact space, where the coset G gamma goes to G gamma G inverse. And if you push the push forward of the measure is an IRS supported on the conjugacy class of gamma, or the closure of the conjugacy class, and it noted mu gamma. So every lattice or every conjugacy class of lattices defines an IRS, which if the lattice is gamma, then I denote it by mu gamma. Conjugated lattices correspond to the same measure. And so you see that an IRS is also a generalization of lattices. And there is a procedure of induction. So if you have an IRS inside a lattice, then you can induce it to an IRS in G. So in particular, every normal subgroup of a lattice correspond to an IRS in G. So you can, if you develop the theorem of invariant random subgroup, you can prove results about normal subgroups of lattices and so on. Let me give another very general, or in a sense, the most general example. Example number 3. Let X M be a G space, a probability measure preserving G space by a result of Varadarajan by compact model theorem. The stabilizer of almost every x in X is a closed subgroup in G. So you get a map. This gives a map from X to the space of closed subgroup, where a point goes to its stabilizer. So the push forward of M is an IRS. That's that's a relation between invariant random subgroup and PMP action. If you want, you can say that to study probability measure preserving action, you can divide this theory to 3 parts: the study of orbits, the study of stabilizer, and the interplay between them, the cycles. And this is, here we focus on the study of stabilizer. And then you have a proposition, or let's say a theorem. This theorem was in a paper by 7 authors, which I'll mention also other theorem later about invariant random subgroup. I'll just write the initial: Miklos Abert, Nicolas Bergeron, Ian Biringer, myself, Nikolai Nikolov, Jean Rambalt, and Ido Samet. And okay, this is one of, there are many theorems in this paper, and this is one. It says that every IRS, any arrays in this way correspond to some PMP action. So for any IRS, you can find a probability measure preserving action such that the stabilizer is the IRS. It's not a very hard theorem, but it's not completely trivial. The first thing you want to do is to take the IRS itself. You already have a PMP action, the action of G by conjugation on the space of closed subgroup, and you have a measure, which is the IRS. But then you see that the stabilizer will not give you the original IRS, but the normalizer. The stabilizer of any point is the normalizer of it. So you have to play a bit and get this theorem, but you see that, so yeah, so basically to study IRS is the same as studying stabilizer in PMP actions. And there are different actions that give you the same IRS. It's not unique by any way. Yes, so these are some standard and general results. Yeah, so let me now move to semi-simple Lie group. So you see that IRSs generalize lattices, and one thing you can do is there is a very rich theory, developed theory about lattices in Lie groups. You can start to generalize it to IRSs, to try every theorem about lattices to prove for IRSs. The other thing is now, when you look on all IRSs, you get actually some space. The space IRS G is the space of all IRS in G plus the weak star topology. So now it's a space of measures on the space of the compact space of all closed subgroup, the space of invariant measure. If you want the space of IRSG, you can view it as the space of probability measure on the space of closed subgroup of G, which are G invariant. And with the weak
I
start.
have a question.
Yeah.
I have a question. Can I ask?
Yeah, sure.
Yeah, this is about the previous theorem. So, so is it true that the ergodic PMP actions go to the ergodic IRSs and vice versa?
Yes.
Okay.
Can I ask something?
Yeah.
Yeah, so you said that every IRS corresponds to the PMP action. So if you take lattice gamma and you take mu invariant measure on G mod gamma, you get an IRS. So, but what is the PMP action for? I mean, G acting on a
Sorry?
I don't know. So you took, if you take a lattice gamma, you got an IRS, right, on sub G.
Yeah.
So what would that correspond to the action of G on a space?
It will be the only invariant measure on the supported on the conjugacy class of the lattice.
Oh.
So you can describe it geometrically. Yeah, okay. I don't want to go in too much into it because I want to describe some real theory.
Yeah, sure, no problem.
Yeah. Yeah, I can refer you later to some lecture notes and where these things are described. So anyhow, by the Banach-Alaoglu theorem, do you hear me?
Yes, we hear you now.
Yeah, okay. So for instance, if you take SL2R and you restrict to a surface group, and by this you can get some compactification of the moduli space corresponding to the IRS. But again, so just from the fact that this is compact, you can use it in several ways. Okay, let me start by saying one result. So one theorem for lattices that you can generalize to IRS. So Borel density theorem. So Borel density theorem, if you say that if G, let G be, actually from now on, let me assume from now on that G is a simple Lie group. Let G be a simple Lie group. Anything I say can be generalized to semi-simple Lie group. Most of what I say can be generalized to semi-simple analytic group over non-Archimedean local field and so on. But let's assume we're in a simple Lie group like SLNR or SONR. And Borel density theorem would say that if you have a subgroup gamma, which is cofinite, so G mod gamma is finite measure, which is G invariant, then gamma must be discrete and Zariski dense. And you can generalize this theorem for invariant random subgroups. So let mu be an IRS of G. An IRS of G. Then okay. Then okay. Let's suppose that it has no atoms. So what can be the atom? The atoms could be either the Dirac measure on G or the Dirac measure on the trivial group, because these are the only normal subgroup of G. So let's mu be an IRS on G without atom. Then mu is supported, I mean, almost surely on a discrete Zariski dense subgroup. That's the Borel density theorem for IRS. If you know Fürstenberg proof for Borel density theorem, so the story is that Borel proved this theorem for lattices, a very clever proof, but a year later, Fürstenberg gave a very elementary proof and analyzing some properties of measure on projective spaces, which are invariant under non-compact groups, and the so-called Fürstenberg lemma. And this Fürstenberg proof can be applied also in the setting of IRS. So you get this theorem. I will not, I need 15 minutes to describe the proof. So I will not do it, but you see that this is one of the theorems that you can generalize from lattices to IRS. As a result, we can use it and restrict ourselves to deal with discrete IRSs. So in a sense, we know now that this implies that the space sub GD, which is the space of discrete IRS. And I should tell you what does it mean to be discrete IRS? It means that it's a probability measure that almost surely it gives you a discrete group. So this space is also compact. That's if you think about it, you can add, also you can allow Dirac measure on the trivial group, but you don't add the Dirac, you don't allow Dirac measure on the full group, and then you get the space of all discrete IRSs, a combination of that. And to use it, to prove it, you need a well-known old lemma that G, the point G is isolated in the space of closed subgroup. The space of closed subgroup is a compact group. Okay, we saw some example like for R and R2 that these are connected spaces, but if G is a simple Lie group or semi-simple Lie group, then you cannot approximate it in the Chabati topology by other groups. So it's isolated point. So you can remove this point and you still get a compact space, and then you look at probability measure on that space, and then by the Borel density theorem, every IRS will be supported on discrete groups. So the space of discrete IRS is compact space. So now I can, only from that already I can prove real theorems. So I want to give two examples. I have half an hour, so I hope I will manage. I'll try to spend 15 minutes on each. One of them is to prove the Kashdan-Margulis theorem. That's an old theorem about lattices, which says basically that there is a lower bound on the core volume of lattices. So there is, if you look at locally symmetric spaces, there is minimal covolume. You cannot have, if you restrict yourself to hyperbolic manifold of, let's say, given dimension, let's say 3, then there is some lower bound on the volume. So you cannot have a manifold of arbitrarily small volume, or in other words, more strongly, stronger result that there is an identity and neighborhood in G such that for every lattice, you have a conjugate which intersect this neighborhood trivially. But I will show you that this result becomes very elementary when you generalize it to the compact space of all IRS. So for this, I need to tell you some definition. A family, let's say F of IRS, is weakly uniformly discrete so weakly uniformly discrete if for every epsilon, for every positive epsilon, there is ID neighborhood U inside G. So it's a neighborhood of G, open neighborhood of G, of the trivial element in G, such that for every mu in the family, for every IRS in the family, the probability, the mu probability that a subgroup meets U non-trivially is smaller than epsilon. Okay, maybe it takes a bit, 2 minutes to understand what it means, but it says that, let me read it again. A family of invariant random subgroups, so these are probability measure on the space of closed subgroup which are G invariant, is weakly uniformly discrete if for every epsilon there is U such that for every element in the family, the probability that a subgroup meets U non-trivially is small, smaller than epsilon. Then it's weakly uniformly discrete. And what is the theorem? The Kashdan-Margulis theorem for IRSs. Kashdan-Margulis theorem said following theorem. The family, let's say, let G be a simple group. Simple Lie group. Then the family of all IRS, all discrete IRS. So these are by Borel density theorem. These are all the IRSs which give measure 0 to the full group. So the family of all discrete IRS is weakly uniformly discrete. Why this implies Kashdan-Margulis? Because take epsilon, any epsilon which is smaller than 1, and apply to mu gamma, where gamma is a lattice, you see that there is some neighborhood such that the probability that you meet it trivially is positive. The probability that the intersection is non-trivial is smaller than epsilon, so it's strictly smaller than 1. So the probability that you meet it, so this implies that there is U in G open such that there is such that, okay, such that for any gamma, mu gamma that the intersection with U is trivial, this is smaller than 1. This is smaller than epsilon. So the intersection is trivial, is positive. So in particular, you have a conjugate of gamma that intersect U trivially. So that's Kazhdan-Margulis theorem, and it's actually a bit stronger. It gives some effective version of Kazhdan-Margulis theorem, but I will show you now that the proof is really few lines. So I'll move to the other board and show you that it's sufficient for a complete proof. I want to show that the space of all discrete IRs is weakly uniformly discrete. Okay. So I want to show that. So to prove. So G is a simple Lie group. Let UN be a descending sequence of compact ID neighborhood such that the intersection of UN is a trivial element. So basically, if this is G, then you have U1, U2, and so on. The intersection of all of them is the trivial group. These are compact neighborhood which go smaller and smaller. If you want, you can take a metric and the closed ball of radius 1/n. This will be UN. Let Vn inside sub G Vn will be the set of all gamma in G such that gamma intersect UN trivially. So I claim that this is open. Vn is open. It's a lemma. The proof is 3 lines. It relies on the fact that G has no small subgroup, so it's a connected Lie group. So G is a Lie group, and so this, for instance, this is not true in non-Archimedean groups, but here it's true. Vn is open. It's clearly the union of Vn is the space of all discrete subgroup of G. Because you see, what is Vn? Vn is the set of all discrete group that intersect trivially some open neighborhood. Every discrete group intersect trivially some open neighborhood. And if the UN go smaller and smaller, then if you start with a discrete group, at some point it misses or intersect trivially the UN. So that's completely elementary. Everything I said is completely elementary. Maybe you need to meditate a bit about it, but it's completely elementary. So now fix epsilon, any epsilon, and then let, let's say, kappa n epsilon be the set of all mu IRS, discrete IRS of G, such that the mu, the probability of Vn is yes, such that the probability of Vn with respect to mu is bigger than epsilon. It's the same n. Here, here. So this is also open. This is basically because the Chabati space is metrizable, then you can prove that such a space is open. The space of all measure that gives a certain open set more than epsilon is an open set in the space of measure with a weak topology. But then you see that the union of k and epsilon, so the union over n, is everything. Every discrete IRS, if you fix a discrete IRS, there will be some small neighborhood such that you intersect it with the non-trivially, the probability is smaller than epsilon. So if you fix the measure and you fix epsilon, then you can find a neighborhood. So this is basically what is written there. And then by compactness, Borel density theorem told us that the space of discrete IRS is compact. So compactness implies that there is n0. So that's an open cover of a compact space such that k n0 epsilon is the full space. Okay, maybe this was a bit fast, but that's a complete proof of Kasdan-Margulis theorem for invariant random subgroups, which is stronger than the original Kasdan-Margulis theorem for lattices, which in particular implies that there is a lower bound on the volume of, if you want, any hyperbolic manifold or any locally symmetric space of a given type. So it's, in a sense, it's a strong theorem, but a very elementary proof because of the way we look on lattices as special point in the point of invariant random subgroup. So you can find, I wrote a paper about this. The proof in the paper is half page. So if this was too fast, then look up. I have a paper about Kasdan-Margulis theorem for invariant random subgroups. And this is the argument there. And yeah, so that's one maybe indication that invariant random subgroup are good tools to study lattices, but this is an old theorem that we're reproving, maybe a shorter proof. But we can also say new result about lattices, which were not known before. So let me now give you another theorem. I spent the last 15 minutes trying to describe another theorem which was not known before. Again, I just intuitively say things. To give a formal proof, maybe I need half an hour, and but I'll describe. So here is the theorem. Okay. Okay, the theorem. So now let G be a simple Lie group of rank, real rank at least 2. So what's called high rank group. These are groups that are known to be rigid in many ways, more rigid than rank 1 groups. They have property T. They have superrigidity, like some rank 1 group, but they are even more rigid. And okay, let X be G mod K, the symmetric space. Associated to G. Then I say the following. Okay, by the way, if M is an X manifold, X orbifold. By this I mean a manifold which is locally isomorphic to X. So M is of the form X mod gamma, where gamma is discrete. And if you have R is some real number, then M less than equal to R, it's the subset of all points inside M where the injectivity radius is smaller than R. So what does it mean? So if I have a manifold and suppose R, this is R, I look at points where I can embed such a ball. So in this picture, I see that MR is let's say this part. I can embed a ball, which would be contractible, but here say I cannot. So this is the R thick part. The R thick part of the manifold. Okay. So the result that we proved in the paper with the 7 authors that I mentioned before, the following. Again, Hubbard, Bergeron, Biringer, myself, Nikolov, Rambal, and Samet, and we proved that for every epsilon and R, there is V such that if M is X manifold with volume M at least V, then the volume of the thick part divided by the volume, or let's say the volume of the thick part is at least 1 minus epsilon times the volume of M. Okay. The probability that the point is in the thick part is at least, in the R thick part, is at least 1 minus epsilon. It means that when you look at lattices or of higher and higher co-volume, M is X manifold, let's say, of finite volume. With volume, let's say.
Yeah, so Tsachik, quick question. So do you have any assumptions on G for this theorem, or is it any semisimple group?
Now I assume that G is a higher rank. G, let's say,
Okay.
and the rank of G is at least 2. Yes, you can generalize it to, let's say, you can generalize it to semi-simple group, but you always need rank at least 2, and we also need Kashdan property T. We don't know it for, let's say, irreducible manifold of type H2 times H2. So yeah, so let's suppose simple group of rank at least 2. It's not true in rank 1. In rank 1, you can imagine manifold which are everywhere thin, like a manifold with very large volume, but the injectivity radius is bounded, like bounded by by fixed number, and the volume is arbitrarily large. So you can have this in rank 1. You cannot have it in higher rank. In higher rank, when you have a large manifold, it will also have large. In most points, it will have large inductivity radius. That's how manifold in high rank. And this result is there are many applications of it. You can actually study asymptotic invariant of, let's say, many analytic invariant, L2 invariant. In fact, you can show that you can associate a Plancharel measure to every, let's say, uniform lattice, a relative Plancharel measure, and you can show from this result that the relative Plancharel measure, if you normalize them properly, they converge to the Plancharel measure of G. And in particular, one consequence corollary is the following. So let Mn be X manifold of finite volume. Let's say X manifold such that the volume of Mn goes to infinity. Then the Betti number of Mn, the normalized Betti number, converge to a limit which is called the L2 Betti number of X, but this is a complicated way to write 0 basically, because beta, bk of X, where bk of X is 0 if k is not the middle dimension, and it's something which you can compute, I will write it in a complicated way, but it's the Euler characteristic of the compact dual divided by the volume of the compact dual. But it's something, some number where when k equals the dimension over 2. So in particular, if X is odd dimensional, like the symmetric space of SL3R, which is 5-dimensional, then all of them are 0. There is no even dimension. And by this result, it means that if you have any sequence of lattices in SL3R, such that the volume goes to infinity, which means basically any sequence of lattices, which different lattices, because for any given volume, there is only finitely many up to this volume, up to conjugation. So for any sequence of lattices, if you look at any k, then the Betti number divided by the volume goes to 0. So the Betti number can go to infinity, but slower than the volume, sublinearly in the volume. So that's one consequence. There are plenty of other consequences. I don't have time to say the proof. The proof is not very difficult. Again, by looking at invariant random subgroup, it's some compactness argument, but also some we use also property T, Kashdan property T, and we rely on a result of Stuck and Zimmer, which I should maybe also explain. So a key result here is the following theorem of Kashdan of Stuck and Zimmer. Stuck and Zimmer prove the following theorem. Let G be simple Lie group of at least 2. Then or let X be a PMP G space. A probability measure preserving G space. Then X is then the action is either the action is either free, essentially free, meaning that the stabilizer of almost every point is trivial, or essentially transitive. Meaning that there is an orbit of full measure. So that's how. That's all the every PMP action of SL3R is either free action, the stabilizer are trivial, or it's the action of SL3R on G mod gamma. That's action of G on G mod gamma. So this is a Stokes-Zimmer theorem. In fact, it's a theorem about invariant random subgroup. You can understand it as a theorem about invariant random subgroup, but they prove it much before people started to study and talk about invariant random subgroups. And it's very useful theorem. So relying on this theorem, we proved this theorem about the asymptotic shape of locally symmetric manifold and orbifold, again using invariant random subgroup. So time is up. I realized that I wanted to say too much about invariant random subgroups. So I spoke too fast. I can assume it was hard to follow all the details. But I wrote a lecture notes a few years ago about application of invariant random subgroup, where I explain in more details both of what I did here and many other results. So if you can look an archive about, I wrote, it's called Lectures on Invariant Random Subgroup. So, you can find it there. Basically, what I'm trying to say is that this is a great tool to study lattices. You can prove new results about lattices and old results in a better way, and stronger results and simpler proof. And so it's very efficient when you focus on lattices and asymptotic invariant of lattices. However, it's limited. And you can understand that it should be limited because the groups that we are interested in, semisimple Lie group, are non-amenable groups. And when you study non-amenable group, and to restrict to invariant measure limits you a lot. So if you want to say more general result about subgroups of semisimple Lie groups, and you want to use the notion of randomness, then you don't want to limit yourself to invariant measure, to invariant random subgroups. So next week, and I will try to be less ambitious and to speak more slowly, and maybe it will be easier to follow. I will describe, I will discuss some non-invariant random subgroups, some new results or new ideas that when you consider random subgroup or random closed subgroup or random discrete subgroup, but in a way that you will not, it doesn't have to be invariant, you can still use it and prove results about general discrete groups, not necessarily lattices, and yeah, and even I will try to tell you that you can even improve this theorem, the theorem that I described here about asymptotic shape of lattices and finite volume manifolds. You can improve it even further if you allow yourself to consider also non-invariant random subgroups. Okay, so I think I was a bit too fast, but yeah, I hope you got something from this, and that maybe I convinced some of you that invariant random subgroup it's a good notion to study and to apply. And but if you have questions, now I can answer. I can try to answer. I don't.
Okay,
Yeah.
I have a question.
Yeah.
So, the theorem you mentioned, the second theorem you mentioned, that implies that, I mean, isn't it equivalent to saying that if you have a sequence of x orbitals which has volume growing off to infinity, then Benjamin-Schramm converges to a uniform unimodular random manifold?
Yeah, this theorem is actually equivalent. It's equivalent, so you still see me. This theorem is equivalent to the following. What is written here? Okay, let me focus. What is written here is equivalently. I didn't have time to explain the notion of Benjamin-Schramm topology and Benjamin-Schramm conversion. Is equivalent to say that Mn converge in the Benjamin-Schramm topology to the symmetric space, to X, to the universal cover. That's actually what. So in fact, there is a notion of Benjamin-Schramm topology, but the Benjamin-Schramm topology on X manifold, X orbifold, is equivalent to the weak star topology on invariant random subgroup. So there is an equivalence between these two topologies.
Yeah, makes sense.
Yeah. Yeah.
Thanks.
Thank you. More questions? Yeah, it was a bit fast. I think, yeah, I should spend 3 hours about the same stuff, and then it would be more clear. But yeah, I wanted to say it's a beautiful notion, and it is a good notion. It has application. So okay, maybe.
Yeah. So Tsachik, I had a quick question. So this last estimate that you have written here, is there an effective version of this in terms of the thick part divided by the volume? I mean, you've shown that it's converging to 1, but how it converges to 1 in volume, or say, are there effective versions of this theorem? Or
Yeah, effective version of that. There are conjectures. In the paper, in the same paper of the 7 authors, we give some effective version when you restrict to congruent subgroups of arithmetic groups. Then you can get some effective version. And in fact, yeah, similar results about effective version, but in a very restricted, much stronger results, but in a very restricted, like a subgroup of GLN Z. You can find in the work of Erez Lapid and Tobias Finis. They study. Okay. Recently, more recently, Tsachik, who is my partner for what I will describe next week, but without me, he proved the effective version of such a result for actually hyperbolic tree manifold. So this theorem is not true for hyperbolic tree manifold, but if you restrict to congruence arithmetic manifolds, it is true, and it's actually more than true. It proves a fantastic effective version of such a theorem in 3 dimensions for congruence arithmetic manifold. So there are some effective results in the literature, but most of the things are open. I mean, I think it's extremely interesting because whenever you prove such an effective version, there are plenty of consequences. So it's extremely interesting, and there are some limited partial success by people. I'm not involved in any of this effective stuff, except that in the original paper we have a section about congruence subgroup of general higher rank group, and there we prove some effective. Yeah.
Okay, thanks, Tsachik. The one other thing is, does superrigidity fit in? This is a philosophical question. Does superrigidity fit into the story of IRS in some form, or are these two completely orthogonal directions? Or yeah, I mean, this is a very general loose question. So
the normal subgroup theorem, which is not superrigidity, but it's another theorem of Margulis. It's actually it's really a theorem about IRSs, and you can see that Stuck-Zimmer theorem, for instance, it's some generalization of normal subgroup theorem.
Right.
I will describe next week is another generalization of the normal subgroup theorem. So the normal subgroup theorem fits very well in this theory. Superrigidity, in certain places we use in the proof superrigidity, not in that paper, but in other paper we use superrigidity sometimes, but I don't. Yeah.
Okay, so let me try to make this question a little more precise. Is the notion of a commensurator of an IRS, does it make sense?
The notion of
commensurator?
Commensurator. I need to think about it. Maybe. You mean commensurate or superrigidity?
Yeah.
It's a good question. I don't have a good answer. I never thought about it. With Anders, which I'm happy to see came to this talk, we have a joint paper with Anders about commensurate or superrigidity, and superrigidity for it wasn't about invariant subgroup at all. Yeah, but so in a sense, superrigidity for commensurator is the easiest case to superrigidity. And you ask if there is if there is an analog for IRS. It's a good question. I don't know. I never thought about it.
Okay. So yeah, let me see. So final chance to ask questions. Yeah, and anybody else? Yeah. So yeah. We've held you up for, I think, what, already 10 minutes beyond the thing. So let's thank Tsachik and look forward to next week. Thanks a lot, Tsachik.
Next week.